Hi, students. This is a presentation to hit some of the important points of Chapter 4 and to really kind of connect the dots between some of the chemistry and some of the context in which which is being taught in Chapter 4. So Chapter 4 is all about climate change. And so we're going to talk a little bit about air and how light interacts with air and what that has to do with some of the chemical concepts that you're supposed to learn. So we learned in previous chapters about how there are lots of different kinds of light and they have different energies. And we know that visible light is what we can see, and depending on what's absorbed, that's what color, that determines what color we will be able to see. So if one color is absorbed, then the opposite color is what we see. So we talked about that a little bit. And we also talked about ultraviolet light and how that has some good properties for helping with vitamin D, but it also can cause skin damage. So in this chapter, we're going to focus on infrared, which is on the other side of visible light. So it's a little bit lower energy. And you can see just like ultraviolet light is broader than visible, infrared is too. So there's a lot of different wavelengths of infrared light. So let's think about how light interacts with matter. So I have over here on the right a molecule that just has 3 atoms in it. And this arrow that's pointed at it is representative of light hitting this. So what happens when an X-ray hits this molecule? So an X-ray or ultraviolet light, sometimes they can break apart the molecule. If the molecule remains together, what will happen is that an electron will be ejected from the molecule. And so this electron can go on and react with other things, which is why these high energy particles can be dangerous because of the reactions that are produced, or the leaving electron can weaken the molecule so it can fall apart. So here we can see an example of a high energy beam of light breaking apart a molecule, as with ozone. All right, now let's say we have visible light and this interacts with the molecule. So why does the light get absorbed, but the molecules aren't really changed? We still have the same material. So what happens is the electron will start to move away from the atom and then just kind of fall back into place. And when it falls back into place, then we get color released. And so this is what happens when we have like fireworks or flames that are different colors. The light is being released as visible light when those electrons drop back into place. So they've been moved within the atom, but not enough that they leave the atom. All right, so infrared is going to hit our molecules and it's going to cause vibrations. So my animation here is just kind of a slow version of this. And we'll look at a better example in a few minutes. And then microwaves are going to cause the molecule to spin. And again, kind of hard to draw on PowerPoint. You'll see a better example in a few minutes. So we have lots of different ways that light can interact with matter. Anytime the matter changes, that means that light is absorbed. And when it's absorbed, it's not passing through to the other side. So that's the first thing to remember. The second thing to remember is that light is energy, and that energy has to be conserved. So it's going to turn into some other form of energy. It might be turning into visible light instead of another form of light, or it might be turning into motion, either the motion of an electron leaving the atom or the motion of the molecule. Now, when molecules are moving or atoms are moving, that's going to produce heat. So we're going to focus in particularly on the infrared light, where those vibrations are increasing the motions of the atoms and increasing the heat. So we're focusing on solar radiation, of course, coming from the sun. That's what solar means. And this graphic looks at the different places that solar radiation will go. So the first part, take a look at the arrows that are coming directly from this main beam from the sun. So we have 23% is absorbed into the atmosphere. And so that is largely going to be your infrared light. And then you're also going to have 25% that is scattered off the atmosphere, never even gets down to us. So it gets put out into space. Now, some of it comes down and hits the earth, makes it all the way through the atmosphere, and then is reflected out. In fact, because the earth can reflect some of the sun's light, it reflects enough of it that some of this will hit the moon. And if you look at the moon on a day where it is not a full moon, but it's also not a new moon, you can see the sort of dim shape of the rest of the moon completing the circle of the moon. All right, so we have here 46%, or about half of that, the solar energy comes down to the earth. Now remember, some of that is visible light, and that visible light is going to interact with our eyes and with matter, with plants, doing various things. Some of it's going to be ultraviolet light, and some of it is also going to be infrared light. So what happens when it is absorbed by the earth? Now we're going to move over to the right, and you'll see the red arrows here. Of the light that is absorbed by the earth, heats up the earth. We know concrete, asphalt, they get very hot on a summer day. That heat then can be released, and it could be absorbed by the atmosphere, or some of it is just going to make it all the way out into space and escape the earth. Okay, but of the energy that is released from the earth's surface as heat, a good portion of it, so 37 plus 9 is our 46%. So 37 out of that 46 is a good percentage of that. Most of it, the vast majority, is absorbed by the atmosphere, which means we're warming the atmosphere. And then if we look at the light that is absorbed into the atmosphere, either from the earth or from the sun, so the 23 and the 37, those are the two that are absorbed by the atmosphere. Those together make 60%. And then eventually that gets emitted from the atmosphere back out into space. However, how long this takes really depends on a lot of factors. And one of those factors is the composition of the atmosphere. So for example, the moon basically has no atmosphere. Mars has a very, very thin atmosphere. And so the atmosphere does not retain that heat very well. It very readily is emitted into space. But if we look at Venus, Venus has a very thick atmosphere. There's lots of different kinds of molecules that can be absorbing it. And so it takes a long time for that heat to be released into the atmosphere. And so Venus is very, very hot. All right, so the point here is that the air can be warmed from above by the sun and warmed from below by the earth. And this is just natural warming before we even start talking about the heat that people generate. Okay, so all of this is what we call radiant energy. Remember that the light coming from the sun is mostly going to be ultraviolet, visible, and infrared. So we're not really getting too much from the extreme ends of radio waves and X-rays. It's really kind of that middle area of the spectrum. Visible light isn't a high percentage, but it is the strongest radiation. Okay, and then the highest percentage is the infrared light. So the sun emits many kinds of radiation, but most of it is heat or infrared light. Okay, so we also want to talk about how heat can be transferred. So we've got these red lines here representing solar energy coming down from the sun. And so this is our first type of heat transfer called radiation. So light in the form of infrared electromagnetic radiation is absorbed by molecules. Now, some of this might be absorbed by the molecules in the air, and some of it might be absorbed by molecules on the ground. So you could see one arrow hit an air molecule represented by the black dot. The others ended up going to the ground. Once they are in the ground or in the air, the molecules are going to be bumping into one another. Now, air molecules are pretty far apart, and so they don't bump into each other a lot, but the ground and the water both have the molecules touching one another. And whenever molecules are touching one another, they can conduct heat very well. And so this is how you can get the part of the ground that's in the sun be very warm, conducting heat over to the part that's in the shade. So that's also warm. Now, remember, the air is also going to interact with the surface of the water or the ground. And so as they bump into the ground, they're going to hit those extra warm molecules that are probably warmer than they are, and they're going to start to heat up and move back out into space. Okay, so that's called conduction, when molecules are touching one another and they warm one another up by making them move faster. So more motion, faster motion is more heat. And then finally, we can get convection. So you may have heard of a convection oven. This is an oven that has a fan in it to distribute the heat evenly. So instead of all of the heat coming from either below or above from the burners, the fan moves the air around. And so all sides of your food are cooked at the same time. So there are some natural ways that convection can occur. Ocean currents are convection, where warm water is redistributed throughout the ocean. And then air can also have convection. And the way this works is that the warm air expands, or the molecules get farther apart. And in getting farther apart, they can't really go down infinitely, so they tend to spread upward. Now, the colder molecules that are farther away from the Earth's surface, because remember, in the troposphere, the temperature gets cooler as we go up, those are not moving quite as quickly. And so they, as they slow down, they come closer together and they become more dense and sink down. And so the sinking of the cool air and the rising of the warm air creates a vertical convection. So this is mixing of air. So all of these play a part in how the temperature is maintained or increases around the Earth. And extensions of each of these play into weather patterns and all sorts of things like that. Okay, so we saw in our diagram that heat can be radiated from the Earth's surface. When it does that, some of it is going to get into outer space, but remember, some of it is going to be absorbed by the air. All right, so the next thing I want to talk about is heat capacity. So we think of capacity as how much something can hold. Now, heat isn't really an object or a fluid or anything like that. It's really just a measure of the energy of the motion of the molecules. But when we have different materials, that energy may result in different temperatures, because the temperature is related to the speed of the molecules. And so depending on how fast those molecules are moving, or how much energy it requires to make them move faster, you can have different heat capacities. So heat capacity is how much energy is required to raise the temperature. So two ways we talk about this are specific heat capacity, which is how much energy does it take to raise the temperature of 1 gram. And this is what a calorie is. You've all heard of calories. Small c calorie is the energy that is required to raise the temperature of 1 gram of water by 1 degree. Now, food calories are actually 1,000 calories or a kilocalorie. We can think of it as the energy required to raise the temperature of 1 gram of water by 1,000 degrees, but then we run into the problem of, well, then it's no longer water. Or we could think of it as the energy required to raise the temperature of a liter or a kilogram of water by 1 degree. Okay, so that's one way to think about it. And then in this chapter, we've also been talking about moles as a way of counting the atoms. And so that's another way. Instead of talking about per gram, we might talk about per moles. And this is useful when we're comparing two chemicals that have very different molar masses, because the mass is going to affect the energy that's required to get those molecules moving. So just like it would take a lot more energy to get a bowling ball moving than it would to get a ping pong ball moving, same thing with the atmosphere. So if we're looking at an atom of krypton, which is a noble gas, it's going to require more energy to get moving than, say, a molecule of nitrogen or a molecule of hydrogen. Okay, so remember with our gases, all of the particles are really far apart and they all kind of behave the same regardless of what the mass of the molecule is and regardless of the polarity. And we'll talk about polarity in a minute, but polarity attracts the molecules together, but they're so far apart, they're not really attracted to one another. So let's think about some of the gases that are in air. If we look at air as a whole, its heat capacity is about 29.2. Now, we're not going to really worry about units here, but we're going to just use this as kind of a reference. Now, nitrogen makes up most of the atmosphere, remember, almost 80%. And so the heat capacity of air is pretty similar to that of nitrogen. Oxygen is just a little bit higher. Argon is quite a bit smaller. We'll talk in a minute about why that is. And then if we look at carbon dioxide, it's quite a bit larger than either nitrogen or oxygen. Now, if we continued looking at some of the other greenhouse gases, we have water, which is a little bit higher even than carbon dioxide, and methane, which has in that same ballpark with those. So the reason that these three are considered greenhouse gases is they quite literally absorb more energy. And so the more energy they absorb and the more energy they retain, the less that can be emitted out into space. And so that maintains that higher temperature. All right, so remember, our greenhouse gases are going to absorb infrared light. That infrared light is going to make them vibrate or move around more. And as they are moving more, when they hit other molecules, that extra oomph of vibrating makes other molecules move more, which in turn makes the temperature rise. Now, even though the other gases can't hold as much energy, they can emit infrared light in order to relax down into their normal states. Okay, so that released infrared light turns out to be heat. Okay, so we looked at water, carbon dioxide, and methane. Those were our greenhouse gases. Your book calls these GHGs, and they all absorb infrared light. So what kind of characteristics do they have? They each have more than one bond. And so we can see methane here has 4 bonds, carbon dioxide has 2, and water has 2. And so that's going to play an important role. Now, water is a polar molecule, which is one of the reasons why its heat capacity is a little bit higher than the others. That polarity or attraction of water when we have lots of molecules close together can affect the amount of energy that is absorbed or stored. These other molecules, they aren't polar by themselves, but we can change their shape by pulling on some bonds, but not pulling on others. And when we do that, we create a polar molecule. And you'll see in a minute that this is going to be important for absorbing infrared light. All right. The other thing that this says is it's helpful if it has hydrogen bonds. Now, hydrogen bonding is a special kind of bonding. It's not within a molecule, but it's from one molecule to another. So if we look at this water molecule, the hydrogen and the oxygen here is a very polar bond. The oxygen really, really likes electrons. It's very close to fluorine, and so fluorine is the most electronegative. And so that means that there's this positive charge on this hydrogen on the outside of the water. And that positive charge is going to be attracted to any other polar molecules nearby. So particularly if there are other water molecules, it's going to be attracted to the oxygens, which are very electronegative over there. And that's not going to be the case on methane, because methane and hydrogen both have a very similar attraction to the electrons. And so the hydrogens surrounding methane are not very positively charged. Okay, so why does it matter how many bonds we have? The number of bonds is going to give us the number of ways the molecule can vibrate. Every way that the molecule vibrates, called a mode, absorbs a different wavelength of infrared light. So remember that colors can appear by absorbing, by an object absorbing one color, or by absorbing a whole bunch of colors. And so depending on what's being absorbed, you're going to see a different color. Well, same thing is going on here. We can absorb one wavelength of infrared light or a bunch. So let's say I have just one bond. Then I'm going to have a stretch. Basically, all the molecule can do is get longer and shorter. If I have two bonds, like in the water molecule or in the carbon dioxide, I can have the bonds get longer and shorter, but I can also have a bend, which means I can have the angle between the bonds change. Okay, so I've got the atoms getting farther and closer from each other and the bond angle changing. We'll look at examples of this in just a second. And then if I have 3+ bonds, then I usually have some kind of plane of the molecule, and I can twist that plane around. So that's called a torsion, but it's just another way that molecules can vibrate. Okay, so how do we figure out what's important here? Really simple thing we can do is determine the number of degrees of freedom. So I shorten this to DOF, and this is 3N. N is the number of atoms. So if I count how many atoms are in the molecule and multiply that by 3, that gives me my degrees of freedom. So what does that mean? Each atom can move in 3 directions. So it can move up and down, side to side, or in and out of the closer and farther from you. And so each of those motions represents the 3, and then we multiply that by each of the atoms. So if all of the atoms are moving in one direction, let's say they're all moving in to the left, then really the whole molecule is moving to the left. And so we call that a translation. If we're just moving the whole molecule, that's a translation. And it doesn't really take infrared light or visible light to cause that to happen. Another thing that can happen is a rotation. So maybe we have a central atom that pretty much stays where it is, but the outside atoms kind of move in opposite directions such that they are twisting around the molecule. So we have some rotations. Now our translations can happen in any direction. So the X direction, the Y direction, the Z direction. And our rotations can happen in those directions too. So there are 3 of each of those. Our vibrations are pretty much everything else. So that might be where our central atom stays in place, but the 2 outside atoms get farther away from each other at the same time. Or it might be the central atom stays in place, but the 2 outside atoms both move down. Well, if they're both moving down, we're changing our bond angle. Okay. So the vibrations are going to be all of the motions, the degrees of freedom, 3N, minus the 6 things that are not vibrations, the 3 translations and the 3 rotations. Now, there's this kind of side note thing that's only important because we're dealing with carbon dioxide, is that if you have a linear molecule, because the x direction and the y direction are identical, if along the molecule is the z direction, you really only have 2 rotations. And so it's 3n minus 5 instead of 3n minus 6. Okay, so let's take a closer look at rotations, translations, and vibrations. All right, so this is a program called Spartan, and this can illustrate some of the ways that molecules can move. So one thing that I can do is I can take this molecule and move it side to side. So this is a translation, and I could also do up and down. That's another translation, or I could do in and out, farther and closer. That's another translation. I could also take this molecule and have it rotate. And so that's kind of rotating around the side-to-side axis, or the x-axis. I could also have it rotate this way, kind of going around the vertical or z-axis. And then it's kind of hard to do in this program, but I could also have it go around, this way. So those are all the different kinds of rotations. Okay, none of those are going to happen from the absorption of infrared radiation. Now, rotations can be caused by the absorption of another kind of light. Do you remember what that kind of light is? So microwaves cause the rotation of molecules. Okay, now let's take a look at oxygen. So here's oxygen with just 2 atoms. And with just 2 atoms, it only has 1 bond. And so there's only one thing that bond can do. It can get longer and shorter, right? But if I look back at the water, I have 2 bonds. Okay, so let's take a look at the ways that this can move. So this is what's called an IR spectrum, and this shows us what wavelengths of light are absorbed by water molecules. So the highest energy wavelengths are going to show the molecule with different kinds of stretches. So actually, let me do this one first. This is what we normally think of as it's stretching. This is called symmetric because the molecule is doing the same thing on both sides. But it can also do anti-symmetric. So one gets shorter while the other one gets longer. Since these are different wavelengths, that means that's more energy that the molecule can absorb. Okay, now you'll notice there's this other peak down here. This is a bend. So notice the bonds aren't really getting longer or shorter, but the angle between the bonds is getting longer and short, or is getting bigger and smaller. So with our oxygen, we really only had one thing that the molecule could do, but with water, we have 3 things. So just moving from 1 bond to 2 bonds really made a difference. Now, the other thing to notice, if I go back to oxygen, is that oxygen is a very symmetric molecule. We'll talk about why that's important later, but it is also what we call nonpolar. So on here, this spectrum has no peaks, this IR spectrum. Oxygen doesn't really absorb a lot of infrared light because in order for the infrared light to be absorbed in here, we need to have either a polar molecule, which oxygen is not, or a change in polarity. And no matter how long I stretch that bond, I'm not going to make it polar. So let's take a look at methane. So here's methane. And we can think of it as kind of a tripod. This is looking at the bottom of the tripod, and this is kind of setting it up on a tripod. Or we can kind of think of it as having a base on one side with the roof or the peak perpendicular to that base on the top. So different ways of looking at this. Now, this has 4 bonds, right? So you might think, okay, well, if water had 3 different ways that it could vibrate, maybe methane has 4 different ways. So let's take a look. So one way methane can vibrate is for all of these bonds to get longer and shorter. Well, when that happens, that doesn't actually change the molecule's polarity. So that's one way to vibrate, but not really absorbed by the IR. This, however, has the three atoms that are part of the tripod getting longer and shorter, all at the at different times, while one bond kind of stays pretty much in place. Okay, so that's one mode. And we can do this where each of the different atoms is staying in place. So this is kind of four put together, but it is only one wavelength. And we can also have it so that we have that angle changing. So we can get these three almost being flat with the carbon atom and then bending down. Okay, so that's another way that it can bend. And we can do the same thing with each set of three atoms. So not different frequencies, but notice how deep these peaks are. Strong absorption in that area because there's four different ways that we can do that. Okay, so methane has a lot of different ways, 4 over here and 4 over here, and that allows for a lot of absorption of infrared light. Okay, so we looked at the water molecule. Water, remember, has 3 atoms. So let's see if we can find some of the different information that we had about the molecules. Since it has 3 atoms, how many degrees of freedom will it have? Degrees of freedom is 3n, or 3 times the number of atoms. So this is going to give us 3 times 3, or 9 degrees of freedom. Now those 9 degrees of freedom represent different kinds of motion. And we are only interested in the vibrational motion. So we're going to subtract out the 3 translations and the 3 rotations. Infrared light doesn't cause these motions. Now, there is a kind of light that will cause rotations. Do you remember what that was? So that was the microwave light would cause the rotations. All that's left over are the 3 vibrations. So we're showing one of those vibrations here. This is called the symmetric stretch. Now, if we had one bond getting longer while the other one was getting shorter, that would be our anti-symmetric stretch. And then we could also have the bend. We saw an example of that. So 3 different stretches are possible. Each of those absorbs at a different wavelength, which means 3 different places that we can absorb light, absorb infrared light, which in turn translates to heat. Now, if I look at methane, methane has 5 atoms. So the 5 atoms are going to have how many degrees of freedom? Remember, this will be 3n, or 3 times the number of atoms. Okay, so there are 15 degrees of freedom. 3 of those are translations. 3 of those are rotations. So we're going to subtract those out. So we're going to have 3n minus 6, or 15 minus 6, 9 different vibrations. We looked at some of these vibrations. One of them is just all of the hydrogen atoms moving away from the carbon at the same time, and that is symmetric. It doesn't make methane polar at all. It just keeps the same shape. And so that one doesn't really absorb the infrared light. But the ones where we have the bending, or we have some of the atoms getting closer to carbon while others are getting farther apart, those are going to be our vibrations that make the molecule more polar. And as they do that, they are going to absorb infrared light. Okay, so let's talk a little bit about polarity. Polarity is the separation of the charge. So molecules, by and large, are neutral, which means they're the same number of protons, or positive charges, as there are electrons, which are negative charges. So even though the molecule is neutral, we can sometimes have the electrons not spaced out evenly. So when they gather in one location, particularly on one side of a molecule, then it can tend to make that molecule more polar. Okay, so let's look at the water molecule. We've got a particulate model of that on the right-hand side here at the top. Okay, and then we have a sketch or drawing of the molecule with some arrows. So the arrows are going to show where the electrons will go. Oxygen, which sits right next to fluorine, really attracts electrons. Only fluorine is better at attracting electrons. And so that means even when it's bonded to hydrogen and sharing those electrons, it's not really sharing them evenly. They're more attracted to that oxygen. And so that side of the molecule tends to be a little bit more negative. We also have two lone pairs there. So you can see on that drawing on the left, the two dots surrounded by a teardrop shape on either side of the arrow. Those are the lone pairs on the structure of the water molecule. All right, so if the top part of the molecule has all of that electron density and a negative charge, the bottom is going to be more positively charged because the nucleus of the hydrogen atoms is going to be a little bit more exposed. Okay, so water is a polar molecule. Now, if I look at carbon dioxide down below, I do have areas of red where it's more negative and an area of blue, which is more positive, just like I did with the water molecule. However, the areas of red are directly opposite one another. And so they balance each other out. It's kind of like tug of war between identical twins. So there is the equal strength of the pull of those electrons in either direction. So if there's a nearby molecule, it's not in particular bonded to one end or the other end of this molecule. This is a non-polar molecule, okay? So this happens because carbon dioxide is a very symmetric molecule, meaning that one side looks like the other. Now, if we look at the water molecule, if left and right do look like each other, but top and bottom don't look like each other. The top has the oxygen, the bottom has the hydrogen. Whereas with the carbon dioxide, because they're all in the line, the top versus the bottom doesn't look any different. Okay, so if it's symmetric in all directions, then that means that we're going to have a non-polar molecule. All right, remember that our different elements have different electronegativities. Fluorine is the most, but we don't deal with fluorine a whole lot. So oxygen is the second most, and that's the one we really look for to see some differences in electronegativity. So if there is oxygen or something near oxygen like nitrogen, and it is not evenly spread out or centralized, then it can cause some lack of symmetry that is going to cause polarity. So on the left-hand side, we have an ammonia molecule, NH3, and ammonia has a lone pair. So you see the oval with the two dots, that's the pair of electrons that are attached just to the nitrogen, and that's very negatively charged. And the other side of the molecule where the hydrogens are is more positively charged, and that points down. Okay, so the top part and the bottom part don't look alike, so we have a polar molecule. Now, if we look at the molecule next to it, boron has the hydrogens spread evenly around it. Notice there are no lone pairs. Okay, so they're all just kind of laying flat out, and there's no top or bottom that can be differently, have different shapes or electronegativity. And so the boron trihydride, because it is symmetric in all directions, because of its balance, it does not have a dipole moment. It is not a polar molecule. All right, so your book talks a little bit about some different molecular shapes. There are a whole bunch of them that we could get into, but we're just going to look at the ones for 3, 4, and 5 atoms. Okay, now with 2 atoms, there is only one thing you can do. You can have a line. When you have 3 atoms, we could have a line or a linear molecule. And that happens when there are no lone pairs on that central atom, kind of like in carbon dioxide. The carbon has no lone pairs. And if that linear molecule looks the same on the left and the right, then that molecule is going to be nonpolar, just like carbon dioxide. So we had that equal tug of war going on there. The molecule down below looks a little bit more like water. So the water molecule had 2 lone pairs on the oxygen. This has 1 lone pair on the tin. SN is tin. So this is tin dichloride. And so that lone pair pushes away the other 2 bonds. And so because it's pushing them away from itself, they get closer together and we get a bond angle that is not 180 degrees. So in this case, it's 95 degrees. Okay, we call this shape bent or V-shaped. Okay, so this happens when their central atom has 1 or 2 lone pairs. So up in the upper right-hand corner, where it says LP, that stands for lone pairs. Okay, so our 2 shapes we've looked at here are linear and bent. Now we've kind of looked at 4 atoms. We saw that with boron in the middle and the 3 hydrogens around it, or in this case, the 3 fluorines around it. There are no lone pairs on the boron, and with no lone pairs, it lays flat, and with it laying flat, it is nonpolar. So it is the same left and right, top and bottom, and just an all-around symmetric molecule. All right, but if we look at ammonia, we get trigonal pyramidal or trigonal pyramidal. Okay, and this is because the nitrogen has a lone pair. So notice the lone pairs are kind of telling us about, is it going to be polar or non-polar? All right, so if I have 4 atoms, I can have, they're both going to be triangles. One of them is flat or planar, and one of them is puckered or pyramidal. And then the last one we're looking at is 5 atoms. And the one we're really concerned about is the tetrahedral shape, like methane has. So you can see the tetrahedral shape here. And just like with the boron trihydride, we don't necessarily have atoms directly across from one another, but we do kind of have symmetry in all directions, that we can kind of turn the molecule over and make it look the same, only with a different atom in that place. So if I take one of my bottom hydrogens and point it to the top, it still looks like the same molecule. Okay, so the tetrahedral, there are no lone pairs on the carbon or the central atom. And then just as a counter example, we could have 5 atoms in a seesaw shape. So this is sulfur tetrafluoride. So there are 4 fluorine atoms. And I couldn't find a picture with lone pairs, but there's 1 lone pair coming out of the sulfur here that pushes the other bonds away from it. And so since it's pushing the other bonds away from it, it creates a polar molecule. Okay, so lone pairs on the central atom, that's going to give us some polarity. All right, so we talked about several things here. Hopefully you remember that infrared light causes vibrations, and vibrations or motion means heat. That molecules have to be polar, or the vibration should change the polarity in order to absorb the infrared light. Okay, so if we have polar molecules, or what we call polarizable molecules, they can absorb this infrared light, which is going to lead to vibrations, which is going to lead to motion, which is going to lead to heat. The shape is going to determine this second part, whether it's polar or not. And so if I have a shape that has symmetry in all directions, and usually this happens when there are no lone pairs on the central atom, then it's nonpolar. Now I can still have a polar absorption of IR if the molecule gets distorted or changes shape when it absorbs the infrared. But initially, it doesn't have any polarity. And then if I want to know how many places something is going to, how many different wavelengths something is going to absorb infrared light, or the number of ways something can vibrate, which all leads back to how much energy is absorbed, that is determined by the number of bonds. And we can calculate that using the degrees of freedom and the translations and the rotations. Okay, so all of this leads us to understand that when we have our major components in the atmosphere, nitrogen and oxygen only have one bond and we can't make them polar. Argon, the next most abundant, is just one atom, so it doesn't have any vibrations at all. All of those things allow us to see why those particular gases don't absorb as much energy as the molecules methane, carbon dioxide, and water.